Chapter 6, Section 4. Fundamental Theorem of Calculus. Fundamental Theorem of Calculus. Two parts to this theorem. The first part is derivative with respect to x of the antiderivative of t dt from any constant to any function of x. This theorem says the derivative and the antiderivative cancel each other out. The result of these operations is just this integrand, just the integrand right there. But the t gets replaced with this upper limit. I like to say the t takes a hike. In its place, whatever's up here. And we also multiply by the derivative of that upper limit with respect to x. We'll see how this works when we look at a few examples. The second part of the theorem is the integral of a function of x, dx, from a to b will equal capital F evaluated at b minus capital F evaluated at a, where the derivative of capital F of x is this integrand in lowercase capital x. We'll look at a lot of examples to see how we use both parts of this theorem, the fundamental theorem of calculus. Start with page 306, number 2. Page 306, number 2. Y equals the integral from 2 to x of 3t plus cosine t squared this only thing squared here is the t, not cosine t, dt. The directions are in exercises 1 through 20 on the derivative of y with respect to x. So I would say I took the derivative of the left side of this equation, so I have to take the derivative with respect to x of the right side. So bring this down, dy dx. So here's the theorem. The derivative of the antiderivative of that thing underlined in red, it's just that thing underlined in red. These cancel each other out, derivative and antiderivative. So the result is the integrand, but the t does have to take a hike. In its place, we put whatever is up here in the upper limit. And that's it. We also multiply by the derivative of this upper limit, which is just 1. So that's the answer to number 2. That's simple. It'll take a little getting used to. Let's look at number 6. Given y equals the integral from 4 to x of e to the u from secant u du. So we're going to take the derivative of both sides with respect to x. The derivative of the left side with respect to x would equal the derivative with respect to x of the right side. For x, okay? So the derivative of y with respect to x. Here's the theorem. Derivative, antiderivative. Cancel each other out. The result is just, let's hear whatever variable is here. It's usually t, but whatever it is, whatever variable, it takes a hike. This goes in place of u. U gone, x in its place. We're done. We do multiply by the derivative of that also, for the chain rule. So it's all of this that's written here times 1. And in this theorem, this constant is irrelevant. Any constant, it plays no part in the answer. Just like in the last one, that was a 2, it had nothing to do with the answer. Even if that was a 12, same answer. So now we're going to look at number 10. Y equals the integral cotangent 3t dt from 0 to x squared. So we take the derivative of both sides with respect to x, derivative with respect to x of the antiderivative of cotangent 3t dt from 0 to x squared d by dx. So here we have the derivative of the antiderivative. The result is just this integrated. Cotangent 3t, take a hike, x squared goes in its place. We also multiply by the derivative of whatever this upper limit is. So the final answer to number 10 is dy dx equals 2x times the cotangent of 3x squared. Number 14. Y equals the integral from x to 7 of the square root of 2t to the 4th plus t plus 1 dt, and the directions are to find the derivative of y with respect to x. That would be the derivative with respect to x of the left side. But I want to do something first here. So I'm going to erase this. There's an integral property that you know that says that we can switch these limits of integration, put the 7 down here and the x up there. If we do that, this will be the same as long as we multiply by -1. And the reason we have to do this is the theorem only applies when there's a constant on the bottom, right here, the 7, and a function of x up here. Since it was given like this with the x on the bottom, we have to switch these, and these will be equivalent as long as we negate. So now the derivative of y with respect to x, this negative comes down, brings down. The derivative with respect to x of the antiderivative, 7 to x, square root 2t to the 4th plus t plus 1 dt. So dy dx equals, bring down the negative, the derivative of the antiderivative of radical 2t to the 4th plus t plus 1 is radical 2x to the 4th plus x plus 1 times the derivative of this thing. So we are done. Now we're going to look at number 18. Y equals integral of 3x squared 5x of the natural log of p plus p squared dp. Looking for the derivative of both sides of this, because the derivative of the left side is what's asked for. And once again, I have to erase because that's sorry for doing this first. To use the fundamental theorem where we're finding the derivative of an antiderivative, there has to be a number in the bottom here. So we're going to split this integral. We're going to say start at 3x squared, which is given, and go to any number. Just pick a number out of the blue. Say 5. Now let's say 50. It doesn't matter. Does natural log of 2 plus p squared dp. And we're going to add to that the integral from where this one left off. This one left off at 50. And this is going to end up at 5x because that's where we want it. We want the sum of these integrals to equal this original one. And integrand. So, important property of integrals is these two integrals can be combined as long as the upper limit up here matches the lower one down there. These can be put together to equal the original. This is any number at all as long as the one down here matches. So now, these are going to switch. The 50 is going to go on the bottom, and the 3x squared is going to go on the top. And I'm allowed to do that as long as I negate from plus over. I'll just bring that down. We have a number down there and a function of x up there. All right, now we're ready to take the derivative of both sides. Can we differentiate each term? There's 3 terms here. The derivative of y with respect to x equals negative derivative with respect to x of antiderivative 50 to 3x squared natural log of 2 plus p squared dp plus the derivative with respect to x of the antiderivative 50 to 5x and the natural log of 2 plus p squared dp dy dx equals negative. This is the easy part. The derivative of this antiderivative is just the integrand, as long as there's a number on the bottom and a function of x on the top. It's just the integrand, natural log of 2 plus, but the p has to take a hike. It's usually a t. That's why I said take a hike. In place of t, we put 3x squared. Instead of p squared, it's going to be 3x squared squared. So that's it. The derivative of the antiderivative is just this integrand. Well, not really, because we multiply by 6x. The derivative of this upper limit. Now we're ready to bring down the plus. The derivative of this antiderivative is just because there's a number down here and a function of x up there. The derivative of the antiderivative is just the integrand, natural log of 2 plus, in place of p I have to put 5x, instead of p squared I have to get 5x squared. That. And I also have to multiply by the derivative of the 5x. And there's the answer. We're just going to rearrange it so it looks a little cleaner. Here comes the final answer. Exercise 18. The derivative of y with respect to x equals negative. Let's put this 6x in front. Times the natural log of 2 plus 9x to the 4th. Plus, it's the plus, let's put this 5 in front. Put this 5 at the end, put it in front. Times natural log of 2 plus 25x squared. And that is the correct answer. So all of those use the first part of the fundamental theorem of calculus. The second part is used in exercise 28 on page 307. The integral 3 to the x dx from 2 to negative 1. So we write 3 to the x over the natural log of 3, because the derivative of this thing right here is 3 to the x. So instead of writing plus c, like your formula sheet says, instead of the plus c, we put a bracket with a negative 1 up here and a 2 down here. Does not matter what order these are in. We use them in the order that they are given. This bracket tells us to write 3 to the negative 1 over the natural log of 3 minus 3 to the second over the natural log of 3. Which could be written as 1 over 3 natural log 3 minus 9 over the natural log of 3. To subtract these fractions, I'm going to multiply the second fraction by 3 over 3. Leave the first one alone. Multiply the numerator of this by 3. Multiply the denominator by 3. Now I can combine the numerators. 1 minus 27 is negative 26 over this common denominator. And that's the answer. Now we're going to look at number 32. It says the integral of 2 over x squared dx from negative 2 to negative 1. I want to mention before we do this that in this number 28 we used the third formula on your sheet called integration formulas. Number 32, we're going to push this 2 in the numerator to the left of the integral sign, leaving x to the negative 2 dx to the right of the integral sign. And now we're going to use the first formula on your sheet of integration formulas. It says the integral of x to the n dx is x to the n plus 1 over n plus 1 plus any constant. So the 2 gets brought down. This integral is x to this number plus 1 over the same number I just wrote. Plus c is not used here. Instead we use a bracket with negative 2 and negative 1 attached. All this can be rewritten as 2 over x. Let's say negative 2 over x, because we have negative 1 denominator. And the bracket tells us to replace x with the number up here and subtract. After subtraction symbol, replace the x with the number down here. So this right here is positive 2. That's the subtraction symbol. This is positive 1. And the final answer 1. Number 38. The integral of 4 secant x tan x dx from 0 to pi over 3. First thing is this constant multiple, 4, comes to the left of the integral sign. And we look for a formula. To memorize these soon, someday. Bring down the 4. The antiderivative of secant x tan x dx is secant x plus c. Make this instead of the plus c. Pi over 3 is 0. So 4 secant number up here minus 4 secant number down there. Pi over 3 is 60 degrees. The cosine of 60 degrees is 1/2. The secant of 60 degrees is 2. And the secant of 0 is 1. So the answer is 4. Number 40, the integral of 1 minus radical u over radical u du from 0 to 4. Anytime you see two or more terms in the numerator and only one term in the denominator, you should split this fraction like this. This fraction minus this fraction is the same as the integral method. So you should do this anytime you see a fraction with a one-term denominator. Even when finding the derivatives, this is a good strategy. Derivatives or antiderivatives. Well, now that there are two terms here, you can distribute the integral symbol. You can write the integral of u to the negative 1/2 du minus the integral of 1 du. Because radical u over radical u is 1. The integral of u to this number, the integral of u to the negative 1/2 du is u to this number plus 1 over that same number. Don't write the bracket here. Minus, bring down. The integral of du is just u. Put one bracket attached to this whole thing. You don't need to do these separately. I'm going to replace all the u's with 4 and replace all the u's with 0. The subtraction between. Before doing that, you should notice that u to the 1/2 over 1/2 is the same as 2 radical u. So replace every u with 4, 2 radical 4 minus 4, and minus. Now replace every u with 0, 2 radical 0 minus 0. Square root of 4 is 2 times 2 is 4, minus 4 minus 0, so 0 is the answer. Okay, let's look at number 62. This is on page 308. It says, the integral of f of t dt from 0 to x is equal to x times the cosine of pi x. So before we even read the directions for this, we're going to take the derivative of both sides. The derivative with respect to x of the left side. I'm just writing the left side now with the derivative symbol in front. Has to equal the derivative with respect to x of the right side. The derivative of the antiderivative of f of t dt, you know by now that that's f of x. derivative of the other side requires a product rule. This is saying the derivative of a product. The derivative of a product is always the first times the derivative of the second plus the second times the derivative of the first. So there's the first. This is the derivative of the second. The derivative of cosine pi x is negative sine pi x times pi, chain rule, plus the second. That's the second times the derivative of the first. So f of x equals positive times negative, negative x say negative pi x sine pi x. Put this pi over here way up in front, plus cosine pi x. So we did this. I took what was given, I took the derivative of both sides, because we ended up with f of x equals something, and the question is find f of 4. Now that we have f of x, find f of 4. It's negative pi times 4 times the sine of 4 pi plus the cosine of 4 pi. F of 4 equals, I think the sine of 4 pi is 0. So this is 0. And the cosine of 4 pi would be 1. And you're done. Because it's 0 plus 1. So let's try to get one more in. And I know this is going a little long. Number 44 on page 307. Pi equals cubed minus 4x. An interval from negative 2 to 2. And what we have to do is find the total area of the region between the curve and the x-axis. We're actually supposed to do this without a calculator. I'm going to cheat. I'm going to use a calculator to get the graph so that this doesn't take forever. My calculator shows me that this graph looks like this. It's crossing the x-axis at what appears to be negative 2. Let's see, negative 2 cubed would be negative 8. Negative 4 times negative 2 is positive 8, so that makes sense. Obviously crossing the x-axis at 0. And this also appears to be positive 2. 2 cubed is 8. 8 minus 8, 0. So to find the total area between this curve and the x-axis, we are going to find the area of this part and double it, because we believe this is symmetric, the same area down here. So the area of the red part is going to be the integral of this function. It's the part I'm doing is above the x-axis, from negative 2 to 0. That's the part that's above the x-axis. And we're going to say, if we double that integral, we'll get this entire area. So we're going to distribute this integral symbol, and the 2 and the dx. It goes like this. It's going to be 2 integral x cubed dx minus 8 integral x dx. Don't worry about the negative 2 and 0 right now that are attached here. That's 2 x to the n plus 1, that would be 4 over n plus 1, minus 8. The integral of x to the first dx is x to the n plus 1, that would be 2 over n plus 1. We're using the formula with for the integral of x to the n, both times here, and we're integrating from -2 to 0. Before we plug in these numbers, we can reduce these. X to the 4th over 2 minus 4x squared, -2 to 0. So this indicates replacing all the x's with 0. 0 to the 4th over 2 minus 4 times 0 squared minus, now all the x's will be -2. -2 to the 4th is 16. -2 squared is 4 times this 4. We have 0 minus 0 minus 8 plus 4. So there's a mistake somewhere because we could end up with a negative area. Right, the mistake is right here. When we put -2 in here, 16 over 2 is right. But -2 squared is 4, and 4 times 4 is 16. I'm fixing that right there. Because all this was when I replaced x with 0, top number. All this should be all this when x is -2. -2 squared is 4, 4 times 4 is 16. So, zero minus 0 is 0. This minus distributes, so that's -8, minus a minus, that's plus 16. So 8 is the area of the entire region. That is the correct answer.